So our first recurrence relation example, I guess technically our second, but the first standalone video after the introduction is just a very simple one. This is this recursive function is sum, and all it does is sum up the numbers from n down to technically 0, and return that sum. So pretty straightforward function. And so the first thing we do is we write down our recurrence relation. So we have to say t of, and we'll start with the base case. So t, when is the base case? When n is equal to 0, right? And what is that equal to? Well, in this case, it doesn't really matter. We could just say 1 there for 1 unit of work. Maybe that's 2, but that's not going to make a difference in the long run. Then what's the general case? Well, that's this piece here, and let's say, well, if there's a test, a sum there, and a subtraction there. So let's say there's so this is t of some n. Let's say there is 3 work in that, and then what we do is we make n smaller by 1, so this is the rest of the work is n t of n minus 1. So there is our recurrence relation. And let's expand it a few times. So if we expand t of n minus 1, we get 3, and then this is equal to 3 plus t of n minus 2, and then we can expand it again. We've got 3 plus 3, and then expand the t part, that is 3 plus t of n minus 3. All right, and then we know this is the first line, that's the second line, that's the third line. And so we want to take this all the way down to the ith line. And notice what we've got here. So this should look very similar to the previous example. So we've got now 3i plus t n minus I. And then finally, all we have to do is find I such that it triggers the base case and plug that back in. And just as before, I triggers the base case when it's equal to n. We plug that back in, and we get 3n plus t of 0, which is 3n plus 1, which is in big O of n. And that's it. So because this is so similar to the previous example, it's not surprising that it works out in pretty much the same way. The next example, however, will be much more interesting. This code here is binary search. So we've already looked at binary search, and so we know how it works. The main function looks at the middle of the or first check to see if we have an array of size 1, and otherwise return true or false depending if that element is the thing that we're looking to find. Otherwise, it finds the middle point of the array and then calls binary search on either the first half from beginning to middle, or the second half from middle to end. So what's interesting here is every call to binary search, what happens to the size of the input? The size of the input doesn't go down by 1 the way it did in the previous examples, right? And both of those, n was just subtracted by 1. Here, it actually gets divided in half, so it's n over 2. So we'll see how that's going to play out here in a minute. We start, as we always do, by writing down the recurrence relation. So we've got t, n, right, and we've got a base case, and so taking a look, I don't know, maybe that's 7 amount of work. Getting these constants exactly right is not important. For n equals 1, and otherwise, let's say the work's about 6 plus the recursion here, and this is n over 2 for n greater than 1. All right, so there we've got our recurrence relation down, and the next thing we do is we need to unroll it. So you can say, oops, t n equals 6 plus t of n over 2, and then that expand that t, we get plus 6 plus t. So n over 2 divided by 2 is n over 4. And expand it again. Plus t n over 8. And now we can number these. There's 1, there's 2, there's 3, and what we need to do is get to the ith line. And so we can see the first part of the pattern is fairly obvious. It's just the same as it was before. There are I6s, so that's going to be 6i. Now, here's the tricky bit. What is the pattern going on here? The good news is, once you've seen this pattern, you'll always recognize this pattern. So there are really just a handful of patterns to see that you can recognize. So what is going on here? Well, where do these numbers, how are these numbers changing with regard to I? And if you're really clever, you might be able to figure it out, but I can just tell you, notice that this is 2 to the I, isn't it? Right? Because 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and so on and so forth. So we can now write down that this is t of n over 2 to the I. All right, now the next step is to find I for when it's the base case. And so what we'll do is we want this thing to be equal to 1. So we can actually just solve for that. So before we just kind of immediately jump there, well, obviously I was going to be n. But here, in this case, we'll actually want to write it down. So we've got n over 2 to the I, and that we want that to equal 1. Okay, so, well, just algebra this out, multiply both sides by 2 to the I, you got n equals 2 to the I, and then still more algebra, but a little faster, a little more advanced, we take the log base 2 of both sides. So we've got log base 2 of n equals log base 2 of 2 to the I. And that tells us that I is equal to log base 2 of n, right? Because that's in our log identities. We've got a log of something to a power. That power goes out and these go away. So I is now log base 2 of n, and we go and we substitute that back in here. And what we find is we've got 6. We're going to write, for this class, we're always going to write log base 2 as just LG. That's a standard computer science thing, because log base 2 is such a common logarithm in computer science. The physicists get their natural log as an abbreviation. So we're going to get our log base 2 as an abbreviation. So lg of n plus t of n over 2 to the log 2 of n. Now, hopefully you also remember from your logarithms that when you've got 2 to the log base 2 of something, that just becomes that one thing. So this all is equivalent to n, and so we've got n over n there. So this all breaks down to be 6 log n plus n over n is 1, so t of 1, which we know is 7, from back over here. And that's, of course, what we were hoping to get, because this is in big O of log n. So a little more complicated than the others, but as I said, they're just a handful of patterns that you'll need to recognize. And so as we go forward, we'll be seeing more of those.